Good afternoon, everyone. Welcome to Warwick. I'm Xiaowei Zhou here from Warwick and co-director of the Hub. I will be chairing this session. So this is the second session on the emerging research. We have an excellent program ahead. We will begin with 4 short presentations, followed by 4 in-depth presentations. So this session is really showcase the wide range of work in offshore renewable energy, from fundamental research to real-world engineering challenge. So I hope you enjoy this session. We will have some time for questions at the end, so please bear those in mind as we go along. So, okay, now let's get this session started with the 4 short presentations. So each speakers will introduce themselves and their work within 1 minute. Emma, over to you.
Thank you very much. Hi everyone, I'm Emma Edwards from the University of Oxford. Sorry, put my slide up. There we go. And I'm going to be talking about our recently awarded Flex Fund called SurfWind, Surrogate Enhanced Realistic Wind Loading for Scaled Deepwater Wind Testing. So running experiments is a crucial part of developing floating and deepwater wind. It is extremely important for things that we've been hearing about all day: innovation, reducing uncertainty. But it is an inherently difficult task because of scaling mismatches between wind and wave. A common solution for this is a software-in-the-loop approach, where we replace the turbine with a thruster that is controlled in real time with platform motion. However, most of these approaches use a low-fidelity model in real time, and that really reduces the accuracy of this type of method. Our innovation is to use a machine learning surrogate model trained on high fidelity data before the lab experiments. So this can significantly improve the accuracy and reliability of the physical modeling tests, giving developers greater confidence in their energy yield and survivability predictions. So please do reach out to me on LinkedIn to hear more about the project, and a link to our proof of concept paper is on the board as well.
Hi everyone, I'm a PhD student at the University of Manchester. Along with many here at Supergen, I'm interested in researching one of the more abundant energy sources from waves. Existing wave energy converters use power takeoff systems that are made of metal, which is heavy and increasingly expensive. If we change the power takeoff system to use elastomer materials, which are lightweight and plentiful, we can reduce the cost of some of these converters. Our research is focused on developing the compliant electrode materials and dielectric elastomer generators. And the microstructure that you see shows clean, low-defect interlayer bonding, which supports and improves the reliability of cyclic capacitance behaviors in these materials. And similar research has shown really high energy densities, which is one of the bottlenecks in viability. Thank you.
Okay. Hi everyone, my name is Omar. I'm a computational scientist at Scientific Computing Department at STLC. So we specialize in creating high-fidelity model, numerical model for multi-scale, multi-physics problems. And we are the main developers of high-performance coupling library called MUI. So we use the coupling library MUI to couple OpenFOAM for fluid mechanics simulation with structural mechanics simulation based on finite element method using Phoenix. So we are coupling OpenFOAM with Phoenix to do fluid structural interaction applications. In a project with Airbus, we use this framework to simulate fuel sloshing inside the wing. And now this framework has been tailored for offshore wind turbine as well. Another exciting project we worked on is a coupling between a weather forecasting research model to feed a realistic boundary condition to a CFD model called XCombat 3D. So in this framework, we did the simulation for atmospheric boundary layer over an island in Scotland, and there are multiple domains. The larger domain, which is a low resolution WRF model, and inside there is a high resolution CFD model. Yeah, all these frameworks are open source, and we are happy to reach out. Yeah, thank you.
Hello everyone, I'm Tim. I'm from University of Manchester, currently is a lecturer here. So today we will talk about an experimental result that's been done under the Sea Swallow project. And what we find out is that we try to find some waves and try to look at the loadings on a monopile cylinder, basically. And what to our surprise is that we actually find that apart from a steep wave loading, you have an impact along the wave direction. There's actually another impulsive loading that is in the opposite direction of where the wave is coming. This is somehow to our surprise that we didn't expect such a high frequency loading that it looks almost like an impact, but in the opposite direction of the incoming wave. There's quite a few sort of ongoing investigations, and there's a poster out there in terms of explaining what we believe might be the cause of those backwards impact. And here's sort of videos of the experiment where we capture all those wave fields, and it is those the one that's actually a big bulk of water that going after or in the rear side of If you've probably seen here, these are the bulk of water that's going in the rear side of the cylinder, actually causing these impacts. Thank you so much.
Thank you very much for all the speakers. If you have any questions, please feel free to talk with the speakers of the short presentations at the coffee break. Now we move to the research presentations. The first talk will be given jointly by Professor Maurizio Colu and Dr. Cassia Patrin-Yak from University of Strathclyde.
Thank you very much. So it will be a dual act, should be a triple act with Ajit, but we're already too many here. So EnviroClass, going straight to the vision. So you know probably this already. If you're an offshore wind farm developer, you approach a wind turbine generator OEM and you say, my wind farm is in this area, and in this area I have this average wind speed and turbulence. So I need a class 1B turbine. And in their portfolio, they already say, okay, you need this wind turbine. Quick process, no small, no cost, and they give a design out of a portfolio of existing designs. Different if you talk then to the floating superstructure technology providers. They usually say, they go to them and they say, this is the metocean assessment of the local metocean conditions, but they don't have a portfolio of ready-made platforms. That's because the design is bespoke for every offshore wind farm. We don't have pre-prepared designs. So that takes months and takes usually hundreds of thousands of pounds to come up with, and this slows down all the process. So, and then there is an interaction between wind turbine generator OEM and them to figure out how the tower should be designed to avoid bad dynamics and so on and so forth. So what if we mimic the same process that we use for wind turbine generator for superstructure? So there is a magic thing, the 3 question marks is the magic thing that I will talk about later, that basically you go to them and say, this is where I want to build my farm, and they say, okay, this farm is an environmental class 3, so that's the kind of superstructure that you need. That obviously can accelerate a lot floating wind farm. It can, as you will see, facilitate standardization, mass production, industrialization, and so on and so forth. So the magic thing that we're talking about is this project, EnviroPlus. So again, reiterating on some of the benefits, the basic idea is that you do not design the superstructure for a specific farm, you design it for a zone of the sea. So that means that you pre-design this, you divide the North Sea, for example, in there into zones, and then Stiesdal, Principal Power, and others like them have, through EnviroPlus, they have metocean conditions that they need to design against based on zones. So whenever there is a farm in that area, they approach them and say, okay, this is the superstructure for that area. So again, it's mimicking what happens for wind turbines generators. So in the graph at the bottom left, obviously you may say, okay, if you design for an area rather than a specific farm, you're probably going to over-engineer because you need to cope with all the worst condition in a large area and not the wind farm itself. That is true. So on one side, you augment over-engineering, you augment costs, but on the other side, there is the potential to produce, rather than 30, 40, 50 superstructure, you may be producing 300, 400. Obviously, with scale, you can lower costs, you can increase standardization, there is a gain in cost. So where is that sweet spot? Where is the sweet spot between how large is the area, how much is the over-engineering, how much are the benefits in terms of costs? Through this project, we are aiming at facilitating to find this sweet spot, basically. So this is a rather busy slide, not for 8 minutes presentation, also because there are other slides that Kasia will present, but this is basically EnviroPlus method goes from the raw metocean data that you can get through ERA5 or other means down to the 5th block, clustering. So you are able to cluster the area of the seas based on similarities for a range of conditions, not only wind speed and turbulence level like a wind class, but also significant wave height, wave period, wave direction, wind direction. So you may cluster area of the North Sea and beyond based on similarity of these conditions. Then beyond that, we also pushed it a bit further and we started to quantify the over-engineering costs. So that's, the, if you want, the application.
Okay, so more about the practicalities of how we got everything done. So like Maurizio mentioned, we applied machine learning clustering to identify zones of similar wind wave conditions. And we did that multiple times, every time trying a different number of clusters. So if you just look at the one cluster case, it's not very exciting, it's just one blue patch. But as we start increasing the number of clusters, what we see are more distinct features, like, for example, a clear split between the coastal and open waters, or west and east coast. One thing is worth appreciating here. We start from raw metocean data, apply extreme value analysis, apply machine learning clustering algorithm, and what comes out are physically plausible groupings of the offshore conditions. This basically confirms the first hypothesis that we started with. Now, for each cluster, we can identify the relevant environmental conditions. In the bottom row, you can see wave height against the wind speed. And thin curves represent the site-specific conditions, while the thick curves show something that we termed supercontours. It's basically an envelope of all the thin curves, or like the worst conditions that can happen within the whole cluster. So we can use those as design bases for the support structures. Now, as a floating wind developer, we have two options. We can stick to the traditional model of bespoke designs, and then each platform is very specific, very unique. There's no over-engineering yet. But we also can't standardize. Option B, we design only one platform per cluster, and now in some of the sites we'll have the platforms that are massively over-engineered, but we unlock standardization and benefits of scale. So which option is better? Is it A or is it B? As it usually turns out, it's C. We should balance over-engineering with standardization. So in the middle plot, you can see a map of 3 clusters, green, blue, and orange, with some locations identified for this optimization. And on the right-hand side, these are optimization time histories, or convergence histories, aiming to minimize the mass of the platform, which is a proxy for cost. And if we just focus on the blue cluster, you can see that all the thin curves, which relates to the site-specific designs, are lighter and cheaper than the cluster generic design, which is the thick curve. This is also the case for the orange and green cluster, but the average level of over-engineering varies. So this is a very powerful exercise because we can repeat it for different numbers of clusters. And once we do that, we can note the average over-engineering over the whole domain, over all clusters. And what we find is that with number of clusters increasing, the over-engineering average level decreases. At about 9 clusters, it basically vanishes, which is good news, and confirms our hypothesis as well. So being able to derive this over-engineering curve is basically key to making the EnviroClass method impactful, because it gives a little bit of confidence to the developers that maybe it's worth it to drop the standard site-specific model and shift a little bit towards the more economic option C.
Hi, the next speaker is Professor Emilio Martinez from the University of Oxford.
Thank you very much. Yeah, good afternoon, everyone. I'm Emilio Martinez Pañeda, an academic at Oxford, and also the PI of this flexible fan project, Reliable Corrosion Fatigue Predictions using physically based models. And as you can see in the slide, the project involved a number of industry partners and academic institutions. And I'm very grateful to them and to the Supergen Hub for the support, which basically allows us to take the project beyond what a typical flex fund project would do. So let me start with the motivation, which I think is quite clear. So I think despite impressive progress in the competitiveness of offshore wind, its life cycle management is still in its infancy. And this is evidenced by the short lifespan of offshore wind turbines, 25 years, half of that of a nuclear power plant, and also by the high operation and maintenance costs. And moreover, as you can see in this map, life extension decisions are going to be critical, are going to soon become critical to the UK. And so what basically limits the service life of offshore wind farms is the corrosion fatigue of the support structures, because they are exposed to a very aggressive environment, corrosive seawater environment, and cyclic loading from the wind and the sea. And what happens is this corrosion fatigue is quite a nasty business. What you get is some pits nucleating at the interface between the seawater and the metal. Those pits grow, driven by local chemistry and mechanics, And then eventually you get this kind of peak to crack transition event and the propagation of fatigue cracks that cause the collapse of the structure. So it's quite a complicated problem, and you may wonder how engineers account for that in offshore design. Well, they do that through something called S-N curves, which I'll explain in 1 minute for those of you not familiar with this. It's very simple. You go to the lab, you take a cylindrical bar, you do an experiment where you load it cyclically, and you count the number of cycles it took until failure happened. That gives you a point in this graph. You see here, for a given load amplitude, number of cycles to failure, you get 1 point. You do another test at a different load amplitude, that's another point. And then you do many of these tests, and eventually you have enough to draw one of these S-N curves that tells you a little bit in a conservative way what's going to happen. And then you enter this curve with the conditions relevant to your offshore wind turbine, and then you can determine the number of cycles to failure, and since you know the loading frequency, that gives you an estimate of life. And of course you may wonder here, okay, we know that corrosion accelerates this fatigue damage process, so how do we account for corrosion in these things? Well, we do that by taking into account a knockdown factor, which is not only very empirical, but also has some obscure origin. But then once you do that, then, well, again, you do the same process, and then you get 25 years to that. However, there's a consensus that this method is highly inappropriate because, well, for a number of reasons. One of them is they're very empirical, as I said. The other one is that the experiments that we're doing have nothing to do with reality, right? This is here we're assuming uniform 1D conditions. We have a cylindrical bar, but in reality, corrosion is a very localized process. Also, corrosion is a time-dependent and history-dependent phenomenon, but there's no time anywhere here. And the history-dependent means that we cannot use the superposition principles that the standards recommend, or that the engineers are using on an everyday basis. So that's what it is. But I mean, you need to understand that, of course, corrosion fatigue is a very complex phenomenon, not just solved in academic circles. So industry, of course, had to do something about it, right? They couldn't just wait for us to crack the problem. The good news is that there's an opportunity now to scientifically crack this problem. There's a new class of models that have been developed that allow you to basically tackle the two obstacles holding back mechanistic predictions of this corrosion fatigue. The ability to simulate how this morphology, this corrosion front evolves, and also the ability to simulate all these strongly coupled electromechanical phenomena. Because I said before, those peaks grow driven by local chemistry and mechanics, but the local chemistry and mechanics themselves are very sensitive to the shape of those peaks. And this new class of models is what we call facial models, corrosion fatigue facial models, or multi-physics facial models. And these are models that allow you to simulate how peaks evolve, how fatigue cracks evolve in time, while simulating all the underlying electromechanical processes directly. So you can basically solve this corrosion fatigue problem for mesoscale first principles, without making any assumptions, without relying on fitting parameters. You are solving things as they happen in reality. You have electrochemistry here, you have mechanics, you have microstructure. And this is fundamental work that I did during my Future Leaders Fellowship, and I demonstrated that these models were able to predict a wide range of experiments in corrosion and fatigue across a wide range of materials. And the Flexible Fan project gave me the opportunity to take this fundamental work and apply it to the specifics of offshore wind. And we did that through 3 sub-projects. The first one was aimed at understanding and quantifying the interplay between surface roughness and fatigue life. And this is very relevant for offshore wind because often we have a situation where we have our monopiles corroding, but then we protect them in a different region. So we need to understand this first stage where they were not protected, how this impacted fatigue life. And you can do that basically with developing a methodology that allows you to characterize uniquely any surface roughness state as a function of 2 parameters. And then we combine that with those facial fatigue models that I showed you before. You can see some cracks here propagating, and then we were able to predict failure as a function of surface roughness. The predictions seem to match very well experiments, and we created a map to cover all possible conditions. And in fact, there were some experiments done on samples corroded in seawater, and our maps seem to agree very well with those experiments. The second sub-project aimed at developing a virtual experimental campaign, mimicking those laboratory campaigns that have been instrumental in driving our community like SLIC. And we've shown that the model not only is able to capture the data from those experimental campaigns, but it's also able to simulate other well profiles that were not considered there, and of course in a very efficient and quick way. And the last sub-project is one that I find very interesting because we developed the first model for microbiology-induced corrosion, where we enriched the electrochemical description of our problem to include the reactions happening in these bacteria-rich environments. And I find this one quite interesting because, well, I mean, it's very relevant for offshore wind, of course, because bacteria microbiology-induced corrosion is what triggers localized pitting and corrosion in offshore wind, and we were able to show that the model is able to capture that. You can see here we're able to capture the evolution of the corrosion front, very similar to what I showed you before. You see here pitting and pit to crack transition. We can do this in 2D, in 3D, while resolving the microstructure, we're resolving over periods of decades what is the effect of your sacrificial animal to your cathodic protection degrading in time. So that's all. I'll just finish with a few takeaways. I think there's a big opportunity and need to incorporate the latest scientific tools to bring down costs, either in foundation design and operational management, but also to enable mechanistic, physically based life extension decisions. And in fact, the technology that I showed you now that we developed, I know has been used to inform the life extension decision of Hornslet 1 in North Sea in Denmark. And yeah, the opportunity more specifically comes from this new class of phase field models, so multi-physics phase field models, that basically allow you to simulate this kind of corrosion fatigue directly from first principles, right? Simulating directly or explicitly those underlying physical processes, so that you don't have to make an assumption, you don't have to come up with some magic knockdown factors and that kind of stuff. And hopefully I've shown you that the flex time morning was well spent. We tried to work on 3 fronts. One was quantifying and unraveling the role of the interplay between surface roughness and fatigue life. We also aim at reproducing experimental campaigns, bringing this idea of virtual testing that has been so successful in the automotive and aeronautical industries to offshore wind, and also predicting the effect of localized corrosion, including complicated phenomena such as microbiology-induced corrosion. And the project has ended, but I very much look forward to the future. I think this framework has a lot of possibilities, particularly to engage with many of you. For example, it's an opportunity clearly to engage with the fluid mechanics people, because now we need to incorporate realistic loading histories. We can no longer apply superposition. We know that this is not appropriate. So the fluid mechanics community can provide those realistic loading histories that we can incorporate in our model, and we can see how the corrosion processes evolve depending on the behavior of the sea and the wind. And this, of course, will be very relevant as well for floating technologies, where these corrosion fatigue problems are going to become more and more prominent. And I think my time is up, so I'll just finish. One thing I'll say before I finish: all the codes that we developed in my group, we made them freely available. So all the results that I show you, that you see in the slides, you can reproduce yourself at home, and otherwise let me know. Thank you so much for your time. Thank you.
Thank you very much. In fact, you will share the code. Thank you. Hi, the next speaker is Professor Paul Fromme from University College of London.
Thank you for the introduction, and thank you, the previous speaker, for the perfect introduction to my talk, because as one of the members of the last panel called it, I'm also looking at standard monopile wind turbines. So we're looking at offshore wind turbine monitoring in the context of life extension for these older wind turbine, for which we also had flexible funding from Supergen ORE, which enabled us, obviously, with our postdoc Yin-Sheng Wang, who as always did most of the work, and my colleague Philippe Dufour, to have a look at these and to see if we could actually implement such a monitoring approach. So a lot of the background was actually given previously, and I think for this audience, probably I don't need to spend too much time on it, but as the previous speaker said, a lot of the current monopile supported wind turbines are coming up to the end of their design life, and there is obviously the question in terms of what was discussed this morning: energy security, cost reduction. What are we going to do with these? And obviously lifetime extension is one of the options that is being considered. Obviously it needs to make economical sense in terms of the O&M costs, but also in terms of the reliability, whether we can actually continue to operate these offshore wind turbines safely. So what we wanted to have a look at is actually the monopile part, the embedded part of the support structure, because obviously if you ever think of a very simplified wind and wave loading, that is actually where we have the largest bending moment in these monopiles. That is obviously time varying. and then we obviously have the combined problem of both corrosion and fatigue in these support structures. So the 2 points we looked at in this feasibility study was on the one hand side to see can we actually get these reliability calculations more efficient and accurate, to have a look at these scenarios, and on the other hand side, can we actually use what we call guided waves or low frequency ultrasonic waves to actually efficiently monitor the embedded part of the monopile, because with conventional inspection methods it's very difficult, if not impossible, to get there. So the first part, which is actually what Yinsheng was mostly working on, was in terms of the fatigue reliability analysis. We developed a new method which combined an ensemble of surrogate models with an active learning approach, which we could demonstrate that for an offshore wind turbine, the predictions were actually very accurate and very efficient. So we could actually do a fatigue reliability analysis on a reasonably standard PC in less than an hour, which with standard methods takes significantly longer. The outcomes are probably not that unexpected, that the fatigue reliability decreases over time. But if we look at some of the critical weld locations in the monopile below the mud line, what this model allowed us to do is actually to have a look at if we actually have monitoring data and consider proactive maintenance, how we can mitigate that degradation. For details of the model, I would probably need to refer you to some of our publications here. The second part, which is probably the part I want to focus on today, is actually can we actually get such monitoring data for the embedded part of the support structure, the monopile below the seabed line. So if we zoom in a little bit more, is obviously we have got the monopile typically about 50, for a 5 megawatt wind turbine, which is quite standard, about 50-60 meter in length, about 20-30 meters embedded in the seabed, and it's virtually impossible to get there for a standard inspection. So the idea we are looking at is if we actually put some sensors close to the transition piece, can we actually send a low frequency ultrasonic wave down that monopile and gain information about defects, fatigue, corrosion that are developing in that structure, and just a finite element simulation of how that could work, which is actually the actual dimensions of monopile currently somewhere in the North Sea. And if we have a look, we excite our guided wave at the top of the monopile, and then we can see it propagating downwards along the monopile. Obviously, especially if we have thickness changes between the different sections of the monopile, we do get some reflection, but we can see that we actually have quite a significant pulse propagating all the way down the 60 meter length and back up to where our sensors would be located. And if we have a look at that signal, we can see obviously we do get quite some reflections from the changes in the geometry of that monopile, but that we actually do get quite a significant reflected wave coming back compared to the wave we are sending down there. Now, as ever, finite element simulations obviously simplify the problem quite a bit, which actually is why we actually did some experimental monitoring. Obviously, for a feasibility study, we couldn't quite go out to an existing wind turbine, so we developed a prototype in the lab, but tried to scale it as well as possible to match an actual wind turbine monopile. So we went for a scale of about 25:1, which gave us about a 2 meter monopile, which we made in similar method as a real monopile. So we spanded a steel section, welded together, and thickness changes to mimic what we have in a real monopile. We then put that in a tank, because our fluids people didn't want to let me use their nice wave tanks. Somehow didn't want to have a ton of sand in their wave tank. I don't know why, but they didn't want to do it. So we had the bottom of the monopile embedded in sand. We filled it in water, and we had an access hatch here at the side where we could pump out the water, take away some of the sand, introduce an artificial defect at one of the weld locations, and then basically close everything back up and do a measurement with these ultrasonic waves, where basically we borrowed some commercial pipe testing equipment, which we fixed above the water level, roughly where the transition piece would be in a real monopile. And then we did some measurements on this. The first measurement is how we could actually test such a monopile. So this is sideways, so that would be the top where the transducer is sitting. And the blue signal is basically our main signal, the reflections we're getting back from the monopile. And you can see we get a nice reflection at 2, 4, 6, 8 meters. So in air, we can actually measure that very well. If we actually embed it in water and sand, that amplitude goes down quite a lot, but we can still very easily measure these reflections. I'll need to speed up a bit. So if we do the baseline measurement, obviously we get reflections from the bottom and from some of the thickness changes. But if we actually introduce a defect here, and then actually do the measurement on the embedded monopile in water, we can actually get a very nice reflection of that defect in order to monitor actually such corrosion and fatigue damage in such a wind turbine monopile. And then we can actually have a look at how we can integrate such data into our reliability measurements in order to predict the reliability for lifetime extension. Thanks a lot.
Thank you. Please take a seat. The last speaker of this session is Dr. Wei Tan from Queen Mary University of London. Good afternoon, everyone. Thanks for the introduction. I'm Wei Tan from Queen Mary. Today is really a good opportunity for me to actually engage with the Supergen Hub community. As we all know, most of you already showed the data, like previous speaker showed that offshore wind actually is producing 17% of the UK electricity. Very impressive. Until you learn that actually the rain can quietly damaging the blade over the 2 or 3 years time. Today, I really want to try to help understand why this tiny droplet can damage the wind turbine blade and how we use this knowledge to develop better materials. Given how much rain we have in UK, I think this is a timely research. So let's start with backgrounds. Why the rain droplet can cause such damage? The reason for that is that linear speed at the tip of the blade can actually reach over 100 meters per second. At that high speed, imagine millions of that droplet bombard with the turbine blade. It can cause such significant damage on the leading edge. Eventually, damage the blade, influence the integrity of the structure. Currently, there's many options trying to address these problems, such as PU coating, tape, even aluminium. Actually, most of them failed within 3 years. So really, current standard approach is try and error. Try your solution on the rain erosion test and see how it goes. We cannot really depend on this approach. It's not efficient enough. So really we need to understand the failing mechanism first before we can develop a better material. So what is the mechanism? From our literature understanding and also our computational framework, we identify one of the key failure mechanism is this stress wave. As shown in this graph, we have high velocity liquid traveling at around 100 meters per second, collide with the composites, and it will generate this kind of stress wave like the sound wave, propagating through the solids. And you can, bouncing at the interface. After millions of this drop impact, you have this debonding and erosion happening. And we have established a computational framework basically showing that stress wave traveling, essentially starting with the contact point and gradually go through the solid until you reach equilibrium. The question here is, can we actually change this material to a rubber-like materials, such as viscoelastic behavior? Quickly, you can see the damping behaviors. Not only the stress magnitude reduced, but also how much it can travel is reduced. So this gives us some inspirations. Can we actually develop some soft materials, rubber-like, to damp out the stress wave, therefore extend our wind turbine blade coating? So that's how we try to do here. We start with a relatively rigid elastomer just as a reference point. As you can see, this is an experiment we have done, like with a liquid droplet, single jet hitting on the solid. And we really observe this stress wave propagation as we simulated before. And now we just try a soft elastomer. As you can see, the magnitude of the stress wave has been reduced. Similarly, if you look at the final some of the snapshots, you can see the magnitude and the propagation distance are all reduced. So really, this shows a promising result. But you may wonder, this is still trial and error. How can we really find the best solution to galvanize have the highest damping properties? So this needs a material approach. Basically, we have developed a microstructure such as has, like a composite, has a hard segment and a soft segment. With that combination, we can tune the composition of these two species. Therefore, we can actually tune their damping behavior. We normally quantify the damping behavior with this damping factor, the higher the better, against the frequency. So the idea here, or the real novelty here, is actually we know the stress wave travel in the solid is depending on how quick the liquid droplet, 100 meters per second. It has a frequency around 1 megahertz. So our idea basically is to tune the material such that the peak is basically matching that operational frequency. Therefore, you have a highest damping effect. So that's basically how we tune our material and optimize the material design. And now we want really to test out our material in a real industry relevant environment, not just a single droplet, but millions of droplets. This was the test we did at Energy Technology Center at Scotland. And basically, it created this artificial rain. As you can see here, this droplet hit on the blade profiles. Over millions of this droplet impacts, you could create that X-ray damage, which can simulate in real life like 5 to 10 years. And we can not only do this curved shape, but also a flat shape to basically eliminate this geometric effect, to make things easier to understand. So now we have tried 2 different materials, or more than that, but here I'm going to show you 2 examples. As you can see, the rigid elastomer we have shown before is not really good. After 0.8 million drop in impact, you start to see some damage initiation. And until you see 304 or 5 million, you can see a very big crater. How about the soft elastomer? Now this one, you didn't see any damage until you get to 3.5 million. And you couldn't see using your eye if you're sitting very far away, right? So let's zoom in, and now you can see a better comparison. And there's a big craters and some extra damage due to the randomness of these rain droplets. And for our soft elastomer, almost no damage. And if you want to confirm what happened inside the material, you have to use the CT scan. So basically, in the CT scan, we can see the internal damage basically go through the material. The good news here is we didn't see any delamination. So there was a very good adhesion here. But you see some manufacturing defect, that air bubbles during the manufacturing. So that's understandable. But we still preserve a good adhesion. For the soft elastomers, you almost see no damage on the surface. You still see some initial manufacturing defects, but the magnitude also reduced. So really, the soft material not only have a good adhesion, but also a good erosion resistance. That's what we are looking for. In the end, we just want to compare all the material we have tested and look at their performance. And really, we can see a dramatic increase, almost 10 times higher than the reference materials. So our approach does work, not only in a single droplet, but also in millions of droplets. So with that, I want to just summarize the idea here is trying to damp the stress wave at the right frequency. So that's the whole idea. And the impact of this research is to hopefully we can really implement this approach and make it scalable so that we can let the industry use this material, eventually reduce their operation and maintenance cost, because that's cost them 300 million per year for UK wind farm just to repair this leading edge erosion. With that, I want to thank you for your listening, and thanks for my group, my collaborator, and funding bodies. Thank you. Thank you to all the speakers for your excellent presentations. We now have time for questions. We have a question there. That's fine.
Thanks all for the great presentation. I have one question, but from Paul and we both. Regarding the experimental test, both somehow mentioned that it was supposed to be replicating the real condition. But my question is, what was the scaling factor for you? Because, for example, in naval architecture, we have some non-dimensional factors like Reynolds number, Root numbers, and we can scale the model. But what was the scaling factor here? Thank you.
Thanks for that question. So we don't have to worry about Root number for that experiment. So for us, the scaling was about a factor 25:1. Which was for all of the geometry, so diameter, length, wall thickness. The effect in the real part would be to be consistent. We would then need to change the inspection frequency. So we did that frequency at about 25 kilohertz. So we would need to go that factor lower for the real application to then have similar sensitivity to what to predict from these. There's obviously some things which are difficult to scale. So for example, the first prototype we had welded had massive weld caps, which you just wouldn't find on a real offshore wind turbine. You wouldn't have 60 or 70 millimeter weld caps on there. So there's obviously some things which are not perfect.
Thank you for your question. For our case, based on the rain erosion test, we used a sample pretty much 200 times smaller than the real wind turbine blade. Of course, you can imagine there's a lot of environmental condition and also the size effect we cannot really reproduce. But this serves as like a fast screening process where you test that in that lab environment and to select the optimum solution. And then you test that in real wind turbine blades. So that's how actually ORE catapult is trying to do as well. So I think that's the way we save the cost during the design and manufacturing.
Okay. Sorry. I'll try again, sorry. Can I just really commend you for the piece of work you've done that? I know firsthand how leading edge erosion is such a massive issue in offshore wind and also on onshore wind as well, so really interesting to hear about that and the work you're doing. When it comes to test facilities, you just mentioned the offshore renewable energy capital there, and you mentioned the test facility used in Scotland. Can you explain, as an example, why did you choose that test facility in Scotland as opposed to the test facility at the Blythe site? Because as I understood, that was one of the leading sites for leading edge erosion testing.
Thank you for your questions. Really, actually, there's 2 points here I want to mention. Firstly, is we were funded by the Henry Royce Institute Industry Collaboration Program, where we wrote a proposal with Energy Technology Center. So we got a grant, so we have to work together, right? And secondly, I know, ORE Capital has the earliest rain erosion testing in UK, and one of the leading test centers. They have also provide guideline how to test it. But the challenging for that is it has limited flexibility, because we want to test not only flat sample, curved sample, and make some changes during that testing, where ORE normally doesn't allow us to do that, flat testing. So that's basically the limitation, but in the future, when we are looking at the comparison between the two testers, one thing I can share you, actually, the Energy Technology Center was funded by ORE. So they're basically originally the same family, and they're following the similar, test rig development. Any other questions?
Strasbourg University. I have 2 questions, one for Mauricio and Kasia, and one for Lee. So, Mauricio, with regard to your work and division into the sectors, areas, those which were the principal parameters, is it just the wind speed, or there were other parameters taken into account, for example, metal-ocean data, and what exactly, in this case, from metal-ocean data is fed into that model? And in terms of your tests and model, did you take into account dust or sand? Because you won't only have rain, you also have dust, which probably will be sharper impact and probably more effect on soft material. Thank you.
So the clustering method that we have developed by William in Kasia developed is quite flexible, so can take into account multiple parameters. So at the moment it can take into account significant wave height, peak period, wind speed, and directions of wind and waves. But we are already imagining scenarios where you can have different parameters for different applications. You can cluster areas not for designing infrastructure, you can design clustering area for O&M, how difficult is an area to be maintained. It can be a class 2 harshness O&M. So mathematically and numerically the model can mix and match any parameter that you want and can give different weighting to different parameters. If we think about fatigue, there is the famous factor that is the power of the stress oscillation, for example, that can percolate into powers of mid-ocean condition as well. So it's quite flexible.
Maybe just one addition, a bit of acknowledgement, because the fact that we can play around with multiple parameters is enabled by using the diaphragm method for the multivariate environmental contours, which was mainly developed by Ed from Exeter, who's here. So just to acknowledge.
Thank you for your questions on the aspect like considering dust or sand. So this is a problem particularly for onshore wind turbine blades. For offshore, I don't think you can easily see that. Maybe hail,
Even hail is very rare to see in like North Sea because the weather casting, they have records almost 10 years of data. Very rarely to see the hails. So actually, we need to consider that, considering the wind energy not only offshore but also onshore. But to consider that, you need to do this similar test, but now you're adding sand inside. It's more like a water jet cutting, you see. This is very powerful, I agree. It could be much damaging than just a rain droplet. And for that, I think we need to, combine our approach with additional layer, perhaps like hardness, to consider how to against such solid impact as well.
Thank you for your presentation. I was wondering, for the corrosion and fatigue models, do you plan to take into account the imperfection linked to the variability in the manufacturing of the infrastructure?
Thank you for your question, very interesting. Yeah, we know that the fatigue life is very sensitive to any sort of defect. So it could be that you get defects during manufacturing, you get defects as well during the pileup of the process, and then corrosion. In principle, the model, since you're solving things from first principles, so to say, you could incorporate any information that you have. For the time being, we just said, okay, corrosion is likely to become the biggest defect, but of course how you trigger that corrosion or the nucleation of those peats will be influenced by that. Peat nucleation is a complicated problem, quite stochastic, so it's a bit easier to look at the problem already when the peat has formed, but in principle the model could accommodate that, so that's something good to look at. Thank you.
We are running out of time. We take one final question.
Okay, thanks. Just for the environmental class team, I was wondering how many years of data we need to make the clusters significantly, statistically significant. How many spatial points do you consider per, let's say, sea, like the North Sea? How many spatial points do you need to make a model?
So essentially, the more the better. We rely on 43 years of data, I believe. It's based on reanalysis products, which makes it possible. In terms of the spatial resolution, again, we rely on reanalysis data sets which come at about 4.25 degree resolution. So that's what we are bound by. Ideally, we would like a data set which would be much more refined, and then we can start looking into effects over a single large wind farm, which can open new applications to the approach. But currently, we look at it more as a national scale, let's say, which doesn't really require that big of a resolution.
Okay, I know there are more people who want to ask questions. Unfortunately, due to the time limit, we have to stop here. Please do feel free to continue the discussion with the speakers. And thank you very much. And let's thank our speakers.